conservation of linear momentum. Conservation of linear momentum. So we know that momentum is P is equal to m into v. So momentum P is equal to m times v. And consider if a particle of mass m moves with a velocity v, it is carrying a momentum. It is carrying a momentum of m times v. Okay, this is what we are familiar with. So that is what we are saying, that momentum P is equal to m into v. So when a particle m moves with velocity v, it is having a momentum P is equal to m into v. That is, consider a simple example. If a car of mass 1000 kilogram, a car of mass 1000 kilogram moves with a velocity some 54 kilometer per hour. Okay, so here the mass is given and the velocity of the car is also given. So 54 kilometer per hour means it is 54 kilometer per hour into 5 by 18 to convert it into meter per second. Okay, so this will be 15 meter per second. So the car is moving with a velocity 15 meter per second. So now here what will be the linear momentum? So the linear momentum will be P is equal to m times v, which is 1000 kilogram multiplied with 15 meter per second, which is equal to 15,000 kilogram meter per second. So this will be the momentum. Okay, and we are familiar with these type of calculations also. Yeah, now we know that momentum is a vector quantity. Momentum is a vector quantity. That is, it have both magnitude and direction. Magnitude and direction. So be careful while representing these vector quantities, because you have to represent the vector notation for it. And now moving on to the concept of force. We know that this force is equal to mass into acceleration, where this force is a vector quantity again and this acceleration is again a vector quantity. And we know that this acceleration is actually the rate of change of velocity. So this can be written as some delta mv divided by delta t, that is delta of mv. And we are taking this by assuming that mass is not changing. Mass is not changing with t. Okay, that it is clear that. And now it means this f is equal to mv is nothing but momentum. So this is delta p divided by delta t. Here this v has a vector notation. Okay, so this is delta p divided by delta t. And this means that if a force F is acting on a particle of mass m, then according to Newton's second law of motion, we have this F is equal to this rate of change of momentum dp by dt, or which is equal to d by dt of this mv. Okay. Now, if the external force acting on a particle is zero, let me consider it like this. If the external force acting on a particle is zero, we are assuming that the external force acting on a particle is zero. That is, this F is equal to 0. And this implies this dp by dt. We already said that F is equal to dp by dt. That is, this dp by dt will be, that is nothing but d by dt of m into v, and this will be 0 because force is 0, external force is 0. And this implies this p is equal to m times v, and this will be a constant. So since dp by dt is 0 means p is a constant. So this p is equal to m into v is equal to a constant. And this says that in the absence of an external force, the linear momentum of a particle, remains constant. Linear momentum of a particle remains constant. So this is an important point. In the absence of an external force, the linear momentum of a particle remains constant. So up to this time we deal with a single particle system. We are dealing with a single particle. Now consider a two-particle system. Consider a two-particle system with momentum of each particles be P1 and P2. So we are having two particles with a momentum P1 and P2. So in such a case, that we are saying that we are considering two particles with a momentum P1 and P2. Okay. In such a case, if no external force is acting on the system, then this P1 plus P2 is equal to a constant. So P1 and P2 are the individual momentum of those particles, and if there is no external force acting on that system of two particles, then it's a total linear momentum, that is the vector sum of the individual momentum, will be a constant. Or since P1 plus P2 is equal to a constant, we can say that this M1 V1 plus M2 V2 will be also a constant. Okay, so now we deal with a single particle system as well as a two particle system. And now let me consider an n particle system. We are generalizing this to an n particle system, or we are extending the same situation to an n particle system. That is, we have a large number of n number of particles, and let first particle having mass m1, second particle mass m2, third particle m3, fourth particle m4, m5, etc. up to there are n particles having mass, the nth particle of mass mn. And maybe we can assume that this is a rigid body. So means a rigid body means in a rigid body the interparticle distance will be always constant, or the distance of a particle with respect to other particles will always remain fixed. Such a body is called a rigid body. So here all kinds of internal motions are also allowed. In this case, while we are considering this such a system, we are assuming that all kind of internal motions are allowed. It means in between these particles, all those internal motions are allowed. And suppose the particles of the system are interacting. Okay, we are assuming, this is our one of our assumption, that the particles of the system are interacting. So here the particles are interacting with each other. The particles can interact with each other by means of any force. These particles are interacting. The type of interaction depends on what type of particles it may be. Maybe some charged particles, it may interact coulombically, or otherwise if it is some massive particles, it may interact by means of gravitational force. So the interaction depends on the type of particles. Okay, so we are assuming that these particles are interacting with each other, and also we are assuming that it is acted by external forces. So there may be some external forces acting on the system. So while we consider this n particle system, both it have internal forces as well as external forces. Means the particles are interacting with each other, which may result in some internal forces, and some external forces are acting on the system. So this is our assumption regarding this n particle system. Now we are going to discuss the physics of this n particle system. If we consider n particles, let the first particle have a momentum p1 is equal to some m1 v1. The second particle with the momentum p2 is equal to m2 times v2. Third particle with the momentum p3 is equal to m3 times v3. And likewise this nth particle pn has a momentum mn times vn. Then the total momentum of the system, is the vector sum. We had already done it in the case of a two particle system. So here this is about n particle system. The total momentum of the system is the vector sum of the individual momentum. Now this p is equal to p1 plus p2 plus p3 plus etc. up to pn. That is, the total momentum will be m1 v1 plus m2 v2 plus etc. up to mn vn. Now let me differentiate this expression with respect to t. So differentiating this expression with respect to time t. So it will gives the dp by dt is equal to dp1 by dt plus dp2 by dt plus etc. up to dpn by dt. That is, this dp by dt, where this capital P is the vector sum of the individual momentum. So this dp by dt is simply dp1 by dt. It is nothing but f1. dp2 by dt is f2 plus etc. fn. So here where this f1, f2 etc. fn are the forces acting on the particles of masses m1, m2 etc. mn. And so here we get these individual forces f1, f2, f3 etc. up to fn, and these are the individual forces acting on those masses m1, m2, m3 etc. mn respectively. And these forces, as we said earlier, these forces includes both external as well as internal forces. This was our first assumption while we consider the n particle system, that the n particle system, the system itself is interacting with each other which results in an internal force, and some external force is acting on the system. So these forces constitutes the external as well as the internal forces. But according to Newton's third law of motion, the internal forces exists in pairs of equal and opposite forces. So now the thing is clear. According to Newton's third law of motion, the internal forces always exist in pairs of equal and opposite forces. It means they balance each other, and thus do not contribute anything to the total force. So here the internal forces do not contribute to the total force, because the internal force, they balance each other because they are equal and opposite, because they exist in pairs. So according to Newton's third law of motion, while we consider an n-particle system, the internal forces are not contribute anything to the total force. So then what we represent the expression like this: dp by dt is equal to f1 plus f2 plus f3 plus etc. up to fn. This is what we expressed earlier. So here the right hand side represents the total force in the system. So the total force means our initial assumption was that this total force includes internal forces as well as the external forces. But according to the Newton's third law of motion, since the internal forces exist in pairs of equal and opposite forces, they balance each other and thus does not contribute anything to the total force. Okay, so then what will be this dp by dt? The left hand side term dp by dt means the total force acting on the system. This will be only the external force, means the external force only contribute to the total force, since the internal forces will balance each other. So the total force is simply external force. So Fx represents the external force. Now this external force is dp by dt, where p is the total linear momentum of the n-particle system. This is equal to d by dt of, since capital P is P1 plus P2 plus etc. plus Pn, where this P1, P2, P3 etc. Pn are the individual linear momentum of the particles of masses m1, m2, m3 etc. mn. Okay, so from this it is clear that the internal forces cannot change the total momentum of the system. Because being equal and opposite, they produce equal and opposite changes in momentum. So now what we said is that this is an important point. The internal forces cannot change the total momentum of the system. It means to change the total momentum of a system, we should apply some external force. So hence, if we want to change the total momentum of the system of particles, it is necessary to apply external forces on the system. So to change the total momentum, of the system of particles, it is necessary to apply external forces on the system. Okay. Suppose now we discussed already the one particle system and two particle system, and now we are extending the same case to this n particle system. Suppose if the external resultant force acting on a system of particles, that is the n particle system that we are discussing now, is 0. Suppose the external resultant force acting on a system of particles is 0, that is this F external is equal to 0. This implies, we already said that this F external is equal to dP by dt. So if this F external is equal to 0, then this capital P will be a constant. That is, this P is equal to the vector sum of the individual linear momenta, and this will be a constant. Thus, it shows that if the resultant force acting on a system of particles is 0, that is, if the resultant force acting on a system of particles is 0, the total linear momentum of the system remains constant. The total linear momentum of the system remains constant. Okay. So this is very important, that if the resultant force acting on a system of particles is 0, the total linear momentum of the system remains constant, and this is called the law of conservation of linear momentum. Okay. Now let us note this thing. Individual momenta of the particles may change, but their sum, that is total linear momenta remains unchanged in the absence of external force. So this is an important point. The individual momenta of the particles may change. While we consider that n particle system, the individual momenta of those n particle system, that is this mass m1, m2, m3, etc., mn. So the individual momenta of those particles may change, but their sum, that is the total linear momenta, remains unchanged if there is no external force acting on the system. So this is what we are discussing in the law of conservation of linear momentum. Now using this law of conservation of linear momentum, let us consider an example. Okay, so consider a car of some mass 1000 kilogram. This is a car of mass 1000 kilogram moving at a velocity 9 meter per second in the right direction. Okay, so the mass is given, the velocity is also given. Now consider a truck which is stationary. Okay, this truck is stationary of mass some 2000 kilogram. So stationary means its velocity is equal to 0. So here the velocity of car is 9 meter per second, velocity of truck is 0. Now, this car moves in the right direction and let this car collide with the truck. So what will happen? Now this car as well as this truck, this car collide with the truck, and now this is a single entity. Means it has a mass of total 3000 kg, 2000 kg, 1000 kg for car and 2000 kg for truck. Now the single entity, that is this car truck combination, have a mass of 3000 kilogram. Now let me consider the case of before collision. What will be the total linear momentum of this system before collision? So the total linear momentum will be mass of car into velocity of car plus mass of truck into velocity of truck. This will be the total linear momentum of this system before collision. So this will be 1000 kilogram into 9 meter per second plus 2000 kilogram multiplied with 0, and this will be total 9000 kilogram meter per second. Okay, now we know that if no external force is acting on a system, the total linear momentum will remain constant. So in this case, this car collide with the truck and they together form a single entity, a car truck combined entity. In this case, no external force acted on this system. It means that if before collision the total linear momentum is 9000 kilogram meter per second, then after collision also it must have a total linear momentum equal to 9000 kilogram meter per second. So this system must have a total linear momentum, that is total mass multiplied with the velocity of this combined system will be 9000 kilogram meter per second. We know that this total mass is 3000 kilogram into this V is 9000 kilogram meter per second. That is, this velocity V will be 3 meter per second. This 3 meter per second.